Assalamu alaikum. During voice production, the glottal fundamental frequency keeps on changing widely and very rapidly under the very fine control of a system starting from the brain and including the larynx, the vocal tract, the lungs, and respiratory muscles and various other muscles in the neck and the chest. In this presentation, we shall go through the fine control at one principal level, the level of the larynx. During voice production, the vocal folds oscillates rapidly. This oscillation modulates the glottal airflow into a train of air puffs with a certain frequency. You can see the fundamental frequency of the glottal signal in here. This fundamental frequency keeps on changing quite rapidly and sometimes significantly under the control of the same set of laryngeal muscles that can induce all these changes in the fundamental frequency. They do that through two things: the redistribution of the stiffness along the vocal folds and also the changes in the geometry of the vocal fold, the length, the breadth, and the depth. And before going through the individual effect of each laryngeal muscle on the vibrating frequency of the vocal folds, this is just to explain that the control of the natural frequency of the vocal folds, the Eigenfrequency, by the laryngeal muscles is through two things: the redistribution of the vibrating mass of the vocal folds, that is to say, the changes in the vocal folds geometry, the length and the depth of the vocal folds, and through the effect of these muscles on the redistribution of the stiffness of the vocal folds, the stiffness in the core of the vocal folds and the cover. By these two factors, the laryngeal muscles are able to modulate and adjust the required fundamental frequency during phonation. The laryngeal muscles, through their direct effect on several factors, can determine the fundamental frequency required. These factors are not completely independent. They can interplay and affect each other, including the vocal fold stiffness, the intrinsic property of the vocal fold, a physical property of the vocal fold itself, and the tension applied to the vocal fold in terms of either stretching or compressing the vocal fold along its anteroposterior direction, changes in the vibrating mass of the vocal fold, the part of the vocal fold that vibrates during the oscillation can be changed by changing the vocal fold length or the depth of the vibrating ends of the vocal fold, the glottal channel geometry. So vocal fold length is important, the extent and the depth, and also the duration of the vocal fold contact is important, and also factors like the subglottal pressure would also influence the fundamental frequency. We would now go through the effect of individual laryngeal muscles on the glottal fundamental frequency. The lateral crico-arytenoideus is the major adductor of the vocal fold, helped in part by the Inter-arytenoideus muscle. The lateral crico-arytenoideus induces mainly an inward rotation of the arytenoid across the posterior plate of the cricoid cartilage. This inward rotation would help in closing up the posterior cartilaginous glottis. It also would help in the adduction of the posterior part of the vocal folds towards the midline. The inter-arytenoideus muscle connects the posterior parts of the arytenoids and also help in the sliding of the arytenoids towards the midline to meet together in the midline, closing up the posterior part of the glottis. The combined effect of these two muscles is to completely close the posterior glottis, but the mid part of the membranous glottis would still have a small gap, and there will also be a reduced contact and reduced thickness of the medial ends of the vocal folds in this area. This may lead to a breathy voice. This persistent gap would need the activation of other muscles, mainly the vocalis part of the Thyro-Arytenoideus muscle. The direct effect of the lateral Crico-arytenoideus is to adduct the vocal folds by bringing them both towards the midline, helped by the Inter-arytenoideus. But they don't have much effect on the vocal fold length, and also a slight effect on the vocal fold stiffness. They only cause slight medial compression of the membranous part of the glottis and no change in the vertical thickness of the medial part of the vocal fold, the contact area of the vocal folds. This may cause incomplete glottal closure in the mid-membranous part. The indirect effect of these two muscles is to stabilize the arytenoid during its movement to adduct the vocal folds. They stabilize its position over the cricoid cartilage, helped also by the posterior crico-arytenoid, which is an abductor, but it activates during the adduction to help in the stabilization of the arytenoid cartilage. The net effect of the combined activation of the lateral crico-arytenoideus and the inter-arytenoideus is not only to adduct the vocal fold, but also to increase the extent and the duration of the vocal fold contact during vibration, particularly when the subglottal air pressure is increased. They help in keeping the medial ends closer together to sustain the oscillation, and this would lead to an increase in the fundamental frequency. And now the Thyro-Arytenoideus muscle, which forms the bulk of the vocal fold. When activated, the Thyro-Arytenoideus muscle will induce a whole body rotation in the axial plane and the horizontal plane around the axis of attachment to the thyroid and the arytenoid. The whole of the muscle would rotate medially, and this will close up completely the membranous part of the glottis. It would leave the posterior part of the glottis open. To close up the glottis completely, you would need the activation not only of the Thyro-Arytenoideus, but also the lateral crico-arytenoid and the inter-arytenoid, which would close up the remaining posterior part of the glottis. So with any weakness or delay in the action of these three muscles, the lateral crico-arytenoid, the inter-arytenoid, or the Thyro-Arytenoids, there will be a longer open phase of the glottis during the vibratory cycle. The glottis would remain open a bit longer than it should in the vibratory cycle. Normally, the open phase should be 0.40% to 70% of the vibratory cycle. If it is more than 70%, the ratio between the open phase and the total time of the vibratory cycle is more than 0.7, then this would lead to a short contact period between the vocal folds and would allow rapid airflow through the weakened adduction, and this would cause a turbulence. In more severe cases, when there is sufficient separation of the two vocal folds away from each other during phonation, the coupling between the two vocal folds to produce a single fundamental frequency may be weakened, and each vocal fold may vibrate at a different fundamental frequency, leading to biphonation, or a voice containing two distinct fundamental frequencies. The effect of the Thyro-Arytenoideus muscle, the vocalis muscle, on the vocal fold fundamental frequency is a little bit more complex. The Thyro-Arytenoideus muscle tends to stiffen and tense the vocalis muscle itself, the body layer of the vocal fold tissues, the core layer. But at the same time, it shortens the vocal fold length, and this would lead to a decrease in the stiffness of the cover layer of the vocal fold. So there will be an increase in the stiffness of the core layer of the vocal fold and a decrease in the stiffness of the cover layer. This change in the body cover stiffness ratio was noted to increase the duration of the glottal closure and also increase the vocal fold frequency. On the other hand, depending on the depth of the body layer involved in the vibration, the increase in the Thyro-Arytenoideus activation can either increase or decrease the vocal fold fundamental frequency, as we shall see now. The final effect of activation of the Thyro-Arytenoideus muscle on the vocal fold fundamental frequency can vary depending on several specific vocal cord conditions. We'll go through three of these conditions, and the first two specific conditions, they relate to the condition of the vocal fold length. If the vocal fold is elongated, as is often the case during phonation, then activation of the Thyro-Arytenoideus muscle would lead to a decrease in the vocal fold fundamental frequency, a drop in the F0. But if the vocal folds are only slightly increased or slightly compressed, then activation of the Thyro-Arytenoideus muscle would actually increase the fundamental frequency. The other factor is the effect of the activation of the Thyro-Arytenoideus on the vertical depth of the medial edge of the vocal fold during phonation. It would tend to increase the vertical depth of the vocal fold, and also it will produce more medial compression between the vocal folds during their contact. So both these factors, the increase in the vertical depth and the medial compression of the two vocal folds medial ends, would tend to increase the extent and the duration of the vocal fold contact during the vibratory cycle, and both these factors would lead to an increase in the fundamental frequency. So the final effect of Thyro-Arytenoideus on the vocal fold fundamental frequency would vary. Sometimes it would increase, sometimes it would decrease the fundamental frequency depending on the vocal fold specific conditions. We have noticed how a weak or a delay activation of the Thyro-Arytenoideus muscle can produce a long open phase of the glottic cycle with a longer glottal open quotient, more than 70%. On the opposite, if the Thyro-Arytenoideus is overactivated, it can produce a tighter vocal fold approximation during phonation and a shorter open phase. The glottal open quotient would be less than 0.4. The open phase in relation to the total duration of the cycle would be less than 40%. This would give rise to a pressed voice rather than the breathy voice if the open phase is longer. The pressed voice is often characteristic by a second harmonic that is stronger than the first harmonic. The H1 minus H2 would be negative, and this would produce a pressed voice. Somewhere between these two extremes of a breathy voice and a pressed voice is the modal voice or the modal register, which is more commonly used in phonation, characterized by regular vibratory cycles, and a rapid closure of the vocal fold with a more gradual opening of the vocal fold. The opening phase of the glottis would be between 40 to 70% of the glottal cycle. The rapid closure of the vocal folds would produce a harmonically rich voice. This modal voice is produced by the activation of the lateral crico-arytenoid, the inter-arytenoid, and the Thyro-Arytenoid muscles. They would produce a large medial surface thickness and good contact between the vocal fold medial edges, and probably low anteroposterior stiffness of the vocal folds. This would produce a large vertical phase difference between the medial ends of the vocal folds, an appropriately sized closure quotient or open quotient of the glottis, and a small flow rate and strong harmonics. Moving now to the cricothyroideus muscle. The cricothyroideus is formed of two bundles. The vertical bundle is the pars recta, approximates the cricoid and the thyroid cartilage by rotation of the cricothyroid joint. The oblique bundle, the pars oblique, with fibers running upwards and backwards, on activation displaces the cricoid cartilage, and on top of it the arytenoid backwards in relation to the thyroid cartilage. This would lead to a stretching of the vocal folds, increasing the length of the vocal fold, and also increasing the stiffness and the tension in both the vocal fold body and also the cover layer of the vocal folds. The effect of the cricothyroideus on the vocal fold fundamental frequency depends on a special property, physical property of the vocal fold, in that it has a nonlinear stiffness, nonlinear material stiffness of the vocal fold. If the vocal fold stiffness is linear, then an stretching of the vocal fold in one direction would increase the length, but it would not change or increase the stiffness of the vocal fold. But because the material of the vocal fold has a nonlinear property, the stretching of the vocal fold in the anteroposterior diameter would increase both the length of the vocal fold and also the stiffness both in the body and the cover layer of the vocal fold. This is of special importance in the control of the fundamental frequency. The other important effect of the activation of the cricothyroideus muscle is through changing the vocal fold's geometry. This would have its effect on the depth of the medial ends of the vocal folds, the glottal channel, and also on the fundamental frequency. The activation of the cricothyroids would reduce the thickness, the depth of the medial ends of the vocal fold. This will produce a shorter glottic channel with a shorter phase difference between the inferior and the superior parts of the medial ends of the vocal folds. It would make it easier for the subglottic pressure to open up the glottis because it's now thinned out. This will produce a higher vibratory frequency, a very short closed phase, consequently a much longer open phase. This will produce the falsetto-like voice production, falsetto register, mainly because of the shortened phase of closure of the vocal folds, the shortened depth of the medial ends of the vocal folds that would produce a sinusoidal type of waves, very high fundamental frequency and limited number of harmonics. So to sum up the factors that influence the vocal folds contact pattern, the way the medial ends of the vocal folds meet up in the midline during oscillation will depend on things like the degree of vocal fold approximation under the influence of the adductors. This is how the lateral Crico-arytenoideus, the Inter-arytenoideus, and also the Thyro-Arytenoideus can affect the contact pattern. The other factor is the glottal channel geometry, the extent and the depth, and also the duration. The extent and the depth are influenced by, for example, the cricothyroideus muscle that reduces the vertical depth of the glottal channel, and this would lead to an increased fundamental frequency. On the other hand, the Thyro-Arytenoideus would increase the vertical depth of the glottal channel. Another factor is the subglottal pressure. The higher the subglottal pressure, the easier it is to open up a closed glottis during phonation. And the vocal fold stiffness. All these factors would interplay to affect and control the vocal folds contact pattern during oscillation. Because of this nonlinearity in the vocal folds stiffness, the increase in the high subglottic pressure can actually increase the vocal fold stiffness. The increased vibration amplitude driven by the high subglottic pressure would lead to an increase in the stiffness of the vocal folds and also the fundamental frequency. So this combined effect of the contact mode of the vocal folds and the nonlinearity of the vocal fold stiffness can lead to an increase of about 40 Hz in the fundamental frequency if the subglottic pressure is increased. And finally, one more factor that can increase the vocal folds fundamental frequency is the vocal fold collision force during the oscillation. This collision force can increase the stiffness of the vocal fold, and this would also lead to a significant increase in the fundamental frequency of the glottal signal. By this, we come to the end on this presentation on how muscles of the larynx and the larynx physical properties can modulate and adjust the glottal fundamental frequency. Assalamu alaikum.